Hi there and welcome to this video for Senior Physics on Astrophysics. In this video, we're going to be looking at the idea of satellite motion. So basically what is a satellite? Well, a satellite is basically any object which is going to follow a circular path around a planet or a sun. So for example, we've got planets or a artificial satellite. Now remember, they're held in place due to the force of gravity. So because the force of gravity acts at 90 degrees to its linear motion, the result is it produces a centripetal force. And this centripetal force is what's necessary to keep that satellite in its circular path around that planet. Now we know that gravitational force is equal to the moon's weight. So for example, we're going to have the weight force equals mg. But the acceleration due to gravity, which we have on Earth at 9.8 meters per second, is not the same that far from Earth. So as a result, we get the force of gravity will be directly related to the centripetal force, which will also be directly related to the weight of the object. So let's have a look at situations which we've got with respect to satellites. If we get exactly the right speed, we generate a critical velocity. Now this critical velocity we're going to call A in this process. And what it does, it has the ability to overcome gravity and fall into a circular orbit. So for every bit it goes this way, the result is it's pulled down due to the force of gravity. Now remember, that force is actually going to be directly at 90 degrees to the motion. So we push it down this way, which then gives us a vector coming down in at an angle. Now, subsequently, we're going to get all of these angles working together, and the result is it's going to produce a circular velocity, as we can show here with our space shuttle going around with the blue circle. But the problem is, what happens if it's too small? If we don't give it enough velocity, the result is the force of gravity has the effect of pulling it too much. If it pulls it too much in relation to the curvature of the Earth, what will happen is the object will crash into the Earth, as we would find with B and C. So the result is we've got to find the critical velocity at the height that the object happens to be to overcome the effect of gravity. So basically, for every motion it goes this way, it's going to have an equal motion this way, which pulls it at an angle. That angle, subsequently, all the way around, will produce our circular motion. Now, the problem also worth noting is what happens if we actually give it too much velocity. Well, with too much velocity, the result is that space shuttle will fly out and leave the orbit of the Earth. The result is it will either make a bigger orbit, and as a result might be lost, or it might actually just go hurtling out into space because gravity hasn't got enough of a strength to tether it and hold it in place. So when you think about companies like ESA, the European Space Agency, or NASA, when they're putting up satellites into space, we've got to take this into account. How high are we going to put it? And then what velocity do we need to give it in order for the gravitational force which is present in that area or at that specific height to tether it and hold it in its circular path? Remember, a lot of people think that there is no gravity in space. Of course there is, it's just not as strong. So the result is there is always going to be a force of gravity the further you go out. Eventually it will get so less that the effect of that planet will have a very minimal effect. Okay, so we've got the idea that we can require a specific velocity, this critical velocity, but how do we find it out? Well, we know that the centripetal force is going to be equal to the weight force. So our centripetal force is mv squared over r, and our weight force is mg. Now we can cancel out the m's on both sides and then rearrange it so that we get v as our final value. Now this will be our critical velocity. This will be the value that we need to go at a specific height, and that specific height will be the radius of the Earth plus the height that we need to put it into orbit. So we get our critical velocity will be calculated using the square root of g over r. What else are we going to have? Well, we also have to, in order to get out of the Earth's atmosphere, we have to have something called escape velocity. Now, escape velocity basically works on the premise that if I basically fire an arrow upwards, eventually it's going to come down. Why? Gravity is going to grab hold of me. So I've got to accelerate to a speed which is going to be greater than the force of gravity. So, as we state here, there's got to be a certain speed that will cause it to move upward and escape the Earth's pull. The escape velocity for the planet Earth is 11.2 kilometers per second. That means we've got to hit a speed of 11.2 kilometers per second in order to get out of our atmosphere. Now, basically, the formula that we've got in order to work out escape velocity is given by the square root of 2 times g times m divided by r. So we've got two major equations that we need to utilize in order to get a satellite into space. The first one allows us to get out of the atmosphere and overcome gravity. The second one then is to project our satellite, put it into space, give it a linear velocity, which we'll call our critical velocity, at a specific height, which then allows it to actually move around the Earth. Now that's what the space shuttle will be doing. It'll open its door bays once it's got into space. Once it's got into space, it'll hit a certain height. Once it's hit that height, the arm will pull it out of the docking bay, and then it will be given a specific speed, and then it will be released. Then Newton's first law will apply. It will continue unless a force is applied upon it. That force will be at 90 degrees to its motion because it's the force of gravity which will hold it in space. So now you've got to think about all of the different types of satellites we've got in space at the different heights. And what's a hard problem to work out is what level can we put this satellite so it doesn't bang into any of the other debris or satellites that happen to be up there at the time. So this is a question which is every space agency is going to have to deal with. Okay, so I hope you found that useful. Very short unit on satellite motion, but hopefully it will make sense. Do have a look at some of the exercises I've put on this post, have a go at them, and start playing with the ideas of escape velocity and critical velocity. Well, thank you for watching, and I look forward to meeting you again. Bye for now.